uh, right now we are moving on to the another keynote address. Good noon to all of you, according to the Indian time. Good afternoon to all of you. I take immense pleasure in welcoming Dr. Bedir, Chair, Information Technology Group, Wageningen University, Netherlands. Welcome you, sir, for our international conference on contemporary practices of technology and management for economic growth, ICT MEG 2020. I take immense pleasure and privilege in introducing the guest right now. Professor Dr. Bedir received his MSc degree and a PhD degree in computer science, both from the University of Twente, the Netherlands. From 2003 until 2008, he was a faculty member at the University of Twente, after which he joined Bilkent University until 2015. At Bilkent University, he has founded and led the Bilkent Software Engineering Group, which aimed to foster research and education on software engineering in Turkey. Currently, he is a full professor and chair of the Information Technology Group at Wageningen University, the Netherlands. He has more than 25 years of experience in information technology and software systems engineering. He is the author of more than 300 peer-reviewed scientific papers. He has been active in dozens of national and international research and consultancy projects with various large software companies, whereby he has worked as a principal researcher and leading software system architect. Hence, he has got broad experience in software and systems engineering in different domains, such as consumer electronics, enterprise systems, automotive systems, critical infrastructures, cyber physical systems, satellite systems, defense systems, production line systems, command and control, physical protection systems, radar systems, smart metering systems, energy systems, and more. With this, he has ample experience in software and systems architecting, software and system product line engineering, cyber physical systems, model-driven software engineering, aspect-oriented software engineering, global software development, data science, and artificial intelligence. All of these topics he's also actively teaching. He has developed and taught around 20 different academic courses and has provided software systems engineering courses for more than 50 companies in the Netherlands, Germany, and Turkey. He has graduated more than 60 MSc students and supervised more than 20 PhD students. He has reviewed more than 100 national and international projects and is a regular reviewer for more than 20 international journals. He has also been a very active and scientific conferences and organized more than 50 conferences, workshops on software engineering topics. So we are so happy to have you here, sir. I request Professor to take over the session. Over to you, sir.
Okay, thank you very much for the introduction, Dr. Nisha. Can you hear me loudly? Is it okay?
Yes,
do you hear me? You can hear me?
Yeah, I can hear you. Yeah.
Or I can use a different headphone. Otherwise, okay. So I can share the screen now, I guess, right?
Yes, you can. You can share.
Let me just see. Okay, so thanks a lot for the invitation again. Also, thanks to Dr. Raj Kumar Murugesan. We had interactive meetings before. I listened also to the previous talk, very interesting. Lots of ongoing in India, happy to see that. We have also a project ongoing with VIT University. Very nice colleagues, it goes quite well. I will look forward to collaboration to further other collaborations. So, the title of my talk will be Architecting Farm Management Information System. So it's architecture design for farm management information system in the context of precision agriculture. As I was introduced, so this I'm on LinkedIn, so I will be happy to connect with you I'm also on Twitter and also ResearchGate. On ResearchGate, you can download about 95% of our papers. This is our group at the Wageningen University Information Technology Group. We have about 30 members, all in different domains of smart systems engineering. We will still hire 2 or 3 more tenure track professors soon and 2 or 3 postdocs. I'm from the Netherlands. My name is not a typical Dutch name, I should say. I'm from a Turkish immigrant family who immigrated 47 years ago to the Netherlands. I'm one of the first Turkish professor here from Turkish worker families, I should say. I live in the Netherlands for more than 40 years, and so the Netherlands is very interesting country, very nice country, and is doing quite well, very successful, very small country, a lot smaller than India, but it is also a champion in the different domains. For example, it's in #1 in greenhouse horticulture, #1 producer of onions, #1 exporter in values of fresh vegetables, trees and shrubs, producers of seeds, right? #1 in the world, small country, largest auction of flowers and plants. So if you look at the should just close this one. I don't see, sorry. I need to close the, right, okay. If you look at the last year, so it broke again a record of around 95 billion euro export. And that goes actually for the last year. So, and so for the next year, we expect the same always. So, and what is the key, actually, the issue behind this is, of course, the adoption of science, knowledge, and the right strategy. I will not elaborate on that in this talk, because that's also very important. I will focus on a technical part, and actually on a very specific part, which is the architecture design of farm management information systems. You can read more. Yes?
Can we humbly request you to increase the voice of your presentation, sir?
The voice?
Your voice, can it be a little louder, please?
Yes, I will just use another thing. So let me just use that one.
Yes, sir, no
I
problem.
expected this. So we are engineers. We have always a plan B. It should be better now, right?
Yes, sir.
You hear me?
Better. Yes, sir.
It's
It is
much better, right?
It is
Okay.
definitely better, sir. Thanks a lot, sir. Sorry to interrupt you, sir.
No, it's okay. It's good that you said that. So this was my plan B. So, but a better plan. So if you look at this, you can read this in the National Geographic of issue in September 2017 from which actually reports or summarizes the developments in the Netherlands, how this small tiny country feeds the whole world. And one of the issues which you look at, see there's like, this is an example of that report. So for example, this is for the tomato, right? Far ahead all countries, but also on other domains like chilies, cucumbers, and so on, right? So, and the main reason for that, so the brain trust behind these numbers, and one of the indicators is our university, Wageningen University and Research, and also that it's science driven, right? So plus they also discuss on the whole strategy, the alignment of the university industry and the government, like, so we have this, what we say, like the golden triangle, which are very optimally aligned to achieve your high level goals, right? So for success, what we see is like it has two issues: adopting the right technology, but also adopting the right strategy, the right vision, the right mission also, right? And everybody collaborates in the best possible manner, and they are not impeded. You provide the right incentives and so on. quite interesting. Wageningen University. So I'm from this university. Sorry. the trigger behind all this success, it is a very specific university focusing on life sciences, right? So what is life? So plants, animals, human beings. So if you look at the structure of our university, indeed you see like there's a whole department on plant sciences, animal science, environmental, the human being side, social science, and they live in, and they have the food sciences. So all focused on life science. If you enter our city, it's a very small city. It's like 30, 40,000 inhabitants. This is a view of our university, but very successful. And my group is one of the chairs of the social sciences. We focus on socio-technical information systems, AI, smart systems, and so on. So actually, our mission is to develop, to support the research, to advance the research in smart systems development. And so how can we make systems smarter? For this, actually, we see everything as system, right? So we look at the system level, systemic level, holistic level, or if you take that broader system of systems level. That's the first paradigm that we adopt. The second one is like we focus on the software. Software is the brain of everything, and software automates and software makes it smart. In parallel and in complementary to that is the data science AI. Using lots of data, we can create the information that we need, which we can feed to our decision support systems, and which as such will make our system smarter. Of course, we use also another term like socio-technical system. That is part of the systemic view of the systems engineering view, because it's you should not consider it as a single monodisciplinary problem, but it's really a multidisciplinary, but even interdisciplinary or transdisciplinary problems, and which should be also as such tackled like that. Right? So you combine all these disciplines together to solve real practical problems. Information systems. I said I will go talk about farm management information systems. Farm management information system is an information system. Information system typically, and so it's a system in which you use lots of data, you create information out of that, you store that, you process that, etc. Typically, it has two parts. So it has a social part and technical part. A technical part, that's a technology, what kind of big data platform or technology you use. You have a process, that's the technical, but also there's a social part. You have the structure, the people who use it, who develop it, who are organized in some structure, and there's whole interplay between these elements. These colors actually refer to the impact levels, right? So there's there could be a low impact level of technology. This is the impact level 1, but it could also impact how the people should use your system, or that could be our impact level 3. That's the green one, a very radical systemic impact. In any case, so that's the view of information systems that we have. So as such, we consider this from both the technical and the social perspective. And our research is also oriented around these topics. Farm management information system is a management information. So a management information system is an information system. I skipped directly to that. What's that? So it's a management, so with the idea to focus on business, right? So we want to be also successful, economically successful also. And for that, you need lots of information to feed your decision support in order to control, coordinate, analyze, visualize all the information. And as such, with the higher level goals to increase the values and profits of the business. Farm management information systems is just similar, but it is focused on the farm operation, right? So that's our first part, first observation. Second observation is like also the topic of this talk. It is part of a very important element of the precision agriculture. because it includes the software, it includes the data analysis, the AI, the machine learning. Pull it out, and you cannot achieve the goals of precision agriculture. Precision agriculture is like smart or precision farming, precision agriculture, smart farming, and all synonyms. Focusing on the farming domain, you have some input to the business and you have some output. You want to optimize that, and so typically like the crops, the pest, and that the optimize the pesticides, the water resource, and so on. Right. So a third observation here is like another observation, like it is typically it's not one domain itself, but it is the interplay or the integration of all these technologies together, like robotics, drones, Internet of Things, cloud computing, machine learning, software engineering. In our group, we actually focus on all of these domains to make this actually happen, right? If FMIS, farm managed information, what we see, this is not only just for farming domain, but also for all other systems. This was also clear from the previous presentation. So all these systems become smarter. They become smarter because of the advancements in the ICT, advancements in software engineering, systems engineering, and in AI. And what the other issues, like they become connected, right? Or they can become connected. And then we talk about system of systems, right? So we can you have the farm management information system, which is connected to the farm equipment system, with connect with weather data system, seed optimization system, irrigation system, and so on. So they all are created. You see in the middle is the farm management information system. It is connected with all the other systems to create additional value, which cannot be created by any of these individual systems. So as such, so we said like we should adopt, as I said, we should adopt a systemic approach, a holistic approach. The even further approach is the system of systems approach, which is also part of our research. If you look at the architecture, this is from the Harvard Business Reviews, but it's right. So in general, it goes like that. So you have the products, right, and then you could have the product software, product hardware in it, which is connected through the cloud. Typically on the cloud, you store all the data. You have the rules, the analytics, the business logic, and this system is further connected to other systems, right? And we got like the system of systems. And of course, one issue is like the security perspective, which is like cybersecurity, which is part of the whole architecture. Simply put, right? So that's the context of the farm management information systems. What did we say? So it is a management information. It is an information system with the goal to optimize actually your output, input, and so on. It is part of the overall context, and but very important part. And so if we focus on this, and then that's also the topic of my talk today, there are several challenges that we should answer. First of all, if you want to have an FMIS in such a precision agriculture system, what are the features, right? What are the features? Before that, FMISs have already been developed. What were the obstacles so far? So that was the question that we put to us. How to model these FMIs, and I'm now also really considering how to model the architecture design, because if you don't model it, if you don't design it, you cannot provide the rationale, optimize it, your system, analyze your system. So we need explicit models for this. Third question is, what is the required method for designing FMIs? Do these system engineering, software engineering methods suffice? What is the suitable reference architecture? There are plenty of these FMISs, but can we define such a generic architecture? And the fifth question that we consider is like how to ease or automate the development of FMIS. So they are quite related questions. This actually, it was the research line of our group in the last 2 years, I should say. we have parallel research, and this is just one of it. We have also like smart cities, green computing, but this is just one of it. So this has we have published all this work, so you can easily access that. Here are the papers. If you cannot access, I will be glad to share this with you. Just send me an email. Obstacles and features of farm managed information, a literature. What we did, that's a secondary review. I will explain in a minute. Architecture framework, VIT-based food and farm systems, architecture design approach, reference architecture, farmers information systems in precision agriculture. So this is DSL framework, farm managed information. So what we see here is like we have addressed all these 5 concerns. So what were the obstacles, how to model it, what is the method for designing, what is the reference architecture, what is a DSL framework for automating these FMISs. I will shortly explain each of these. Obstacles is quite a lot has been already done in FMIS. So what we did was just a secondary study, a literature review based on a systematic protocol from Kitchenham et al., in which we actually addressed 3 questions. In which domains have been these FMIs been applied, right? Which modeling approaches, and what are the delivery models, were the stakeholders, and foremost, what are the features and the obstacles. And so we looked at the initially 1,000 papers, we reduced them to the final set of 38 primary studies. If you look at the literature, we see like the most of these FMIS have focused on arable farming. So they develop FMIS basically for arable farming. Sometimes they don't mention it, then it's more like general FMIS. Part of it on greenhouse, livestock, multi-purpose, and orchards. So this is the current situation in the state of the art. What about the modeling? So how do they model the FMIS? For this, we have to look in the levels of models, also adopted in the model-driven development community. We can consider 3 levels of modeling. One is sketch-based, like this. You can show your ideas by sketch, but you cannot develop a house based on this. A more precise model is a blueprint. You can hand this over to the developer, which can develop the system according to this blueprint. And the third, the most mature is like the executable. There's no human being involved here. You can hand it over to the machine, which can then generate the more refined models, generate the documents, automatically test your system, check the consistency, and so on. See, so and the question is, what is the current situation of modeling FMIs in the literature? This was actually our assumption. We said like, and this was confirmed. Most of these FMIs are just modeled like box and lines, right? Although it is so important, and then sometimes there are even no diagram. At the most, they have like ER diagrams, or what we know from object-oriented design, class diagram, deployment diagram. But the majority is not well modeled. And that was an interesting issue, which means like that it is not properly modeled. As such, you cannot properly discuss the rationale on your design decisions, analyze your system, to check your system. So that impedes all these motivations. FMIs have been basically single applications. Part of them have been like on platforms. Most of them is like on web, right? That's quite interesting. But this can change, of course. What about the stakeholders? We know the stakeholders. This is important if you develop a system, an architecture. The farmer, of course, governments, agriculture, but we have also identified all other stakeholders which are important to design your system. We have a nice background music, right? What are the features? We have identified these features as well, as reported in the studies. What we see, what we could conclude from this perspective. So the mostly mentioned features were like financial management, reporting, data acquisition, operations plan generation, right? That the top four, these are also like features from ERP systems, enterprise resource planning systems. So most of these FMIs have also built on that ID, but also we also see, of course, more domain-specific features, and these have been actually seen in all different systems. So we couldn't find one complete system in which all these features were actually discussed. So um, so this is explanation of these features: financial management, reporting, data acquisition. I will not elaborate on this, so it should be clear, but it is interesting to see this. So it is like ERP functionality. On top of that, also like crop management, resource management, equipment management, and so on. This was very useful for us because our goal is also to develop a farm management software ecosystem. So now we exactly know what kind of features we need and how to design our system, what should be the our modules and so on. So this is a nice input for us. What were the obstacles of these FMIs? Are plenty of them. So we could identify dozens of them, as reported in these primary studies. But of course, we have prioritized these. Like here, this is the top 10 standardized data formats, which seems to be quite a big problem because typically you have to integrate multiple systems. Of course, the interoperability, right? We have the issues of syntactic interoperability, semantic interoperability, but even process interoperability, but also not just technical, but also non-technical interoperability, like it's not allowed by law or by because of privacy and so on. System integration, it's related to that. Adoption rate, it is a bit less technical, more from business perspective. Again, the cost is sometimes it's too expensive. Farmers cannot pay for that. Incomplete, so it's like FMIs have been developed, but not considering all the stakeholder concerns the required. It's less understandable that is reported. Data size is quite large. They didn't know what to do with that, the accumulation. Connection to internet in rural countries, right? Places or where we have the internet connection is weak. So, and this could be a problem. The farmer skills you because typically, as I said, information system is also a socio-technical system. You develop a system, it impacts the people. That's the social part. They have this, their way of working will change, but they also need these skills. The language and regional that's could be solved easy, and of course security. Which we also had in several of our projects. We want to actually collect all the data, all these systems, but farmers are usually reluctant to share their data, right? So that should be solved, and these are really obstacles. That brings me to the second one. Okay, so what we know, we had a right vision on the features and obstacles. How to model these? I will go quickly over this a bit. For that, actually, again, it's one dedicated paper, architecture framework of IoT-based food and farm management systems. This is focused on architecture, is the gross level structure, systemic structure. So you see every system lives in an environment, but it has also an architecture. And the idea is like, let me model this architecture so that we can actually control, optimize our system. An architecture has an architectural description, and the system has some stakeholders, and which we have identified also in our literature review. So before you design the active, you have to know the architecture and the stakeholder concerns. What are their concerns? Functionality, security. We have to identify all of them. And so based on all these stakeholder concerns, the architect takes all these drivers and designs the architecture. That's the goal. And the design is requires some modeling. And the modeling, the first aspect is like you cannot put it all in one diagram, typically put in multiple diagrams. This is just an analogy of a civil engineering, physical architecting, like you have like floor plan, interior plan, wiring plan. What is the architecture? Well, all of them are the architecture, but each of them have from a different perspective. In a similar sense, we have also the software architecture or system architecture plans, or what we call viewpoints. And so viewpoints. So a viewpoint is just a template, the guidelines for the notation, while a view is an instance of that viewpoint to represent a diagram from a particular perspective. Right, an example in the UML, Unified Modeling Language, you have like viewpoint deployment view, you have the stakeholders concerns, and it says like the notation should be like this, and this is a particular instance of that viewpoint, which is a deployment view for one example case. That's this study. If you, these viewpoints are not designed ad hoc, but typically the several set of viewpoints are designed together, which results, which it together combines an architecture framework. That's what the term that we use, right? So a coherent set of viewpoints defines the architecture framework. There are several architecture frameworks in the literature. In this website, you can, for example, find some of these frameworks. And the idea was, of course, like, is there a file management information system architecture framework? No, there isn't. There was not one yet. And the idea was also, like, are the existing architecture framework sufficient to model the FMI's concerns? In our perspective, they were not, so we needed additional concerns. So what we did was actually develop our own architecture framework, FMI's architecture framework, which consists of these 6 viewpoints. Domain model viewpoint, I will not elaborate on this, but just to ID. So, but this is a viewpoint dedicated for modeling the FMIS, especially for, in this case, it's from the functional aspects. Then the business process hierarchy viewpoint, IoT layer viewpoint, deployment viewpoint, information model viewpoint, and interoperability and endpoints viewpoint. So these have been discussed in this paper. You can check this. This was, I guess, published last year, October 2019. Plus, we have also defined the process on how to use these viewpoints to model the farm management information systems. These have been applied to multiple case studies, like in the animal farming, arable farming, dozens of the case studies, and we checked for the application of this the usage of these elements of these viewpoints to all of these case studies. More details you can read in the paper. So, but this is just what I say is like an approach to model the architecture. Why is this important? Because then we can make our system explicit, we can rationalize, we can justify our design decisions, we can analyze our systems. It's really helped us to design, to improve, enhance the existing FMIS. If you go back to the obstacles FMIS, what we see there is like, there's no single general purpose FMIS, right? So there's lots of variability, there's lots of commonality, but also variability. So if you say like, let's design an FMIS, typically we cannot design a single one. So then we should take really a multi-system scope. And multi-system scope, we directly think about product line engineering, so which considers a set of products for a particular domain. In this case, it's a farm management information system. But here, what we focus first on is one of the key aspects in that, from that perspective, is the designing the product line architecture or reference architecture, which we also did, right? So what is the required reference architecture, and what is the method for designing these FMIS? These were the further questions. So as such, you can also read this in these papers, right? So architecture design approach, design method for IT-based farm management information systems. Here we explain how to actually design such a product line engineering-like method for designing IoT-based FMISs. And in this paper, we directly also discuss the reference architecture for farm management information systems. This is the way how we do this. So that we have reference architecture include several architecture views, because it is like we said, like we have to model this. So we use the views here. So for a particular FMIS, we reuse this reference architecture. We design the application architecture, which reuse the reference architecture views. So for reference architecture design, again, we should not reinvent the wheel. There's some process to follow. We should first check, is there a reference architecture design? And like we did also for the architecture framework. If there's a reference architect, we just reuse that and apply it. If not, if there is one, but if it's not sufficient, we can adapt it. If there's no reference architect, we design a new reference architecture and apply it. In our case, we actually followed this process. We said, is there a reference architecture? Yes, and that was the reference architecture for the IoT reference architecture. But we had to adapt that, enhance that. So that this was the path that we followed, right? And that's this one. So what we said, like, okay, the IoT reference architecture, we are talking about FMIs in the precision farming in IoT-based precision farming. So we have the already reference architecture. So we have to, which consists of the device layer, network layer, session, application business, and the security and management layer. You can look this up. We said, like, well, let's use this. This is quite useful. So no need to reinvent the architecture. And based on that, so of course you can use this reference architecture and then try to define your application architectures. But it's not trivial, right, to make this step. So what we did was like support also the method for customizing, instantiating this reference architecture for FMIs in the precision agriculture. This is the method, so you can read this here. So architecture design approach for IoT-based farm management information system. How does it look like? So this actually follows the two life cycle process that we know from product line engineering. So what we have is like we develop a family feature model. I will explain in the next slide, which actually is a model for the commonality and variability model of these FMIS systems. We develop the IoT FMIS reference architecture. It is a generic architecture, so we develop it for reuse. It is not for particular a single system, but for a family of systems. And based on that, we develop the IoT FMIS components. And there's the second life cycle. You focus on a particular FMIS for one single system. What you do is like you reuse these artifacts which have been developed in the domain engineering phase, right? So you reuse the family feature model to develop your feature diagrams, application feature diagram. You reuse the reference architecture, develop your specific FMIS application architecture, you reuse the components to develop your system. So that's the globally the process. It is totally based on reuse-based approach, because what we say, FMIS, there's lots of variables, there's also lots of commonality. We reuse the commonality and we guide the variability here to develop these systems faster. Feature model, it is like it's a well-known model in product line engineering for commonality variability model. At the top you have the concept, and then you have like you can define several of your mandatory features, but some features could be also like optional, like identities, like hollow bullet, or you could have like alternatives. You can select just one of it, or you could have one or more of it. That's the or diagram. A very successful diagram which is used a lot. There are also variations to this notation, but this is was required to model the commonality and variability. So what did we do? Well, we modeled all these. We provided a feature model, a family feature model for the IoT-based FMISs. Right? This is just part of it. It's a much larger. As you see, like IoT-based FMIS, and you have like typically an data acquisition processing, and so on. The IoT data acquisition, you have the different protocols, and so on and so on. You have the alternatives, the optionals, and this is what we say. It's like a configuration space. Based, if you select all of these features, you actually define one system. I have 6 slides to go, so I hope I'm still in time, right? So this is the commonality variability model, but the second part is the designing the architecture. This is design the architecture. For this, we used multiple architectural views. This is just one view in which we show the decomposition of the FMIS. The colors actually relate to the features in the family feature diagram. And so from this is a reusable decomposition view, family decomposition view. We can take this and define our own application decomposition view. The same, this is another example view of the FMI is a layered view. Not all the details have been given, only for data acquisition application layer, business layer. You see this here we actually define the different modules which are actually allocated to data acquisition layer, to the application layer, and the business layer. And finally, another example is the FMIS deployment view. As you see, it's like, well, if you take this precision agriculture, there are different nodes. You could have like sensors, actuators, vehicles, cameras, drones, satellites. But if you see, like, they are all 0 or more. So it is like to show the options, the variability. You can select it or not. There's a cloud server or not. So based on this, we can have different, multiple different configuration, deployment configurations. Okay, so we have applied this to several cases. This is just for one example, smart wheat production. As we said, all the reusable assets have been developed, like so family feature diagram in which very detailed design of these features, the commonality, variability, representing the configuration space for these smart FMIs, plus all the architecture views. Here we have just shown 3 views: the decomposition layered view, deployment view, which can be reused to develop smart applications. If we take smart wheat production, so what we say, that's the application. So based on this, the requirements for smart wheat production, we defined, selected the features that are required. We reuse that. And once we have selected the features, we can reuse, we can know how to customize, how to instantiate the architecture views. We know, so which in this case, it meant like that we didn't need all these modules here, right? So then this becomes the application decomposition view for smart wheat production. In a similar sense, the layered view becomes specific for the layered view for wheat productions. And finally, for the deployment view, we could reuse the family deployment view to design the application deployment view for the wheat production. In this way, we were able thus to capture all the features, the common variant features, capture the whole architecture. We could model it precisely, and we could design it with the right rationale. And once we were done with this, we could quickly design, derive, and develop these FMIS. And the last part is like how to, okay, that's next, and that will be short, how to ease automate development of FMIS. This is just like recently accepted paper, just like 3 days ago. It will be soon open access. This will be open access, where we focused on developing a domain-specific language framework for this farm management information system. Why was that? Because in one of the obstacles, we said like the farmer skills or understandabilities, and then the idea, how do we address this? Right? And then we said like, okay, let's talk to the language of that domain. That means like, let's design the domain-specific languages so that the domain experts or the stakeholders can easily use this language to design their concerns. So for this, we actually adopt the whole DSL engineering, domain-specific language engineering approach. We identified several DSL decomposition alternatives, and then we ended up with like 3 DSLs, for which we developed the DSLs using the Eclipse eCore tool. And we actually also evaluated this with the group. And this will have a follow-up, because this is now a DSL. Once we have a DSL, the next step is like, okay, how can I use this DSL to generate the documentation, to generate the code, to automatically test the system, and so on. So this again paves the way for further research. So it will be a continuing story. We are ongoing. So what I discussed in my talk today was like, FMIS is an information system, typically integrates software data science. It is a business critical element. If you don't do this well, you cannot achieve your goals. What we did is like we have adopted in the last years a very systematic approach to tackle several of these problems. Like, first of all, we looked at the secondary study to identify the features, obstacles, and the modeling approaches. We had the right insight, and tackled all the problems, the obstacles that remain. So we developed a specific architecture framework to properly model these FMIS. We developed a method to design these FMIS quickly and in a proper way. We designed a reference architecture that can be reused to design an FMIS quickly. Based on the reference architecture, we developed a DSL framework to automate and leverage the development of FMIS. Our future work will further elaborate on this, and we focus on the development of farm management software ecosystems. There's like why we consider this like platform, and everybody will contribute to design this ecosystem. Well, that was my talk. Thank you for listening. I can have questions if we have time.
Yes, Professor Dr. Bedir, thank you so much for an intellectual talk. The floor is open for Q&A. Participants, if you have any questions, kindly post the questions to Professor.
You can access all the papers that I've shown. If not, as I said, I can share this.
Yes, thank you, sir.
Hello. Hello.
Hi.
Sir, this is Rajkumar Murugesan.
Hi. Hi.
Sir, thanks a million for investing your time today.
Thank you.
And you shared a ocean of knowledge with all of us. We need to go back and read every slide of yours, okay, post session, to have a good grip of the entire knowledge, sir. You have given us ocean of knowledge, to be very honest.
Thank you.
Okay, and I will send a wish list and a thanks note by 5 o'clock. Okay, and probably the list of questions also will be shared with you.
Okay, thank
And
you.
we humbly request you to your reply will be shared with the respective participants, sir.
Sure. So I will do.
Yes, sir. So because we had a challenge in the morning, we were behind by about 30 minutes schedule before your session.
Yeah,
Right.
I am aware of that.
Yes, sir.
Yes.
Now, no, the other expert, right, Dr. Martin from Sweden, KTH University, is online now. Okay. So thanks a million again, sir.
Thank you.
Amazing
Thank
session,
you.
sir, to be very honest.
It was my pleasure. Thank you for
Yes, sir.
inviting me again.
Thanks
So
a lot, sir.
thank you. Thanks.
Nisha, ma'am.
Yes, sir. Yes, sir. Thank you, Professor Dr. Bedir. It was a wonderful talk.
Thank
Thanks
you again.
so much. Yeah. On behalf of VIT Business School Chennai, we welcome Dr. Martin. Sir, can you able to hear me?
Yes, I hear you very well. Can you hear me?
Yes, thank you. is Dr. Martin. Hello?
Yes.
Yes, thank you. I take immense pleasure in welcoming Dr. Martin for our international conference, ICT-MEG 2020. We welcome you, sir. I take immense pleasure and privilege in introducing the guest here. Professor Dr. Martin is a professor in embedded control systems at the Mechatronics division of the KTH Department of Machine Design since 2002. He has particular interest in cyber-physical systems, architectural design, system safety, model-based engineering, and co-design of control applications and embedded systems. He has authored and co-authored more than 150 peer-reviewed publications and also been in charge of developing and leading both graduate and continued education courses, as well as the development of new renewed master programs. He has spent time a postdoc at the EU JRC, did a 10-month sabbatical 2011-12 at UC Berkeley, and a 2-month sabbatical in the spring into 2018 at Stevens University of Technology, followed by a 2-month sabbatical again at UC Berkeley in the fall of 2018. In 1996, he co-founded the company Pengho Real-Time Control AB, specializing in advanced tools for developers of embedded control systems and related consultancy. In 1994, he received the SAAB Scania Award for Qualified Contributions in Distributed Control Systems, and in 2004, the ITEA Achievement Award, 2004 contributions in the East WEA project. He served as the technical coordinator of the International IFIS ART MIS project with 21 partners during 2010-2013. Networking and multidisciplinary research have been characteristic throughout his career. From 1999 to 2004, he served as the chairman of the Swedish Real-Time Systems Association, and he has represented KTH as a core partner in the EU networks and excellence in embedded systems design, Artist2 and Artist Design, and in the ATMIS Industrial Association. He is moreover the principal initiative and director of the Innovative Center for Embedded Systems, launched in 2008 of the TECOSA, Swedish National Competence Center on Trustworthy Edge Computing Systems and Applications. Thank you so much, sir, for accepting our invite and being here. Once again, thank you so much. Kindly take over the session.
Thank you very much, Dr. Thank you very much, Dr. Nisha. Can you hear me and can you see my slides?
Yes, sir, very much, sir.
Yeah,
okay.
Perfect.
So thank you again for the very kind introduction and for the invitation. I'm sorry I could not attend all of the previous conference, but I was happy to attend Bedir's talk, and I think and hope that my talk will be complementary to what you have heard previously. So I will reflect on cyber-physical systems, on opportunities and challenges. And as a short complement, just to understand the background, as you heard, I have a background in embedded control systems and mechatronics. My direct research topics are in autonomous cyber-physical systems, and closely related to the previous talk, actually, architecting model-based systems engineering, and in particular, how we make these systems, like automated vehicles, safe and trustworthy. In that domain, we are developing a modeling and simulation platform called ADI. And this talk will leverage a couple of different perspectives. On the one hand, the experiences from my stays in the US that you heard about. I will also leverage experiences from European collaboration. I had the opportunity to be part of 2 road mapping and agenda efforts on cyber-physical systems, investigating what are the challenges and obstacles that we also heard about in the previous talk. And I'll conclude with a few references, but in particular, the platforms for CPS recommendations is pretty recent, and it reviews a number of related agendas in IoT, AI, cyber-physical systems. So it's a pretty recent and I think recommendable overview. And finally, I will also leverage experiences from Sweden and Stockholm, and I will touch a little bit more on some of these initiatives. So, to begin, as a little disclaimer, we heard in the previous talk about systems of systems engineering, and here I would just like to mention that the IEEE Annual Systems of Systems Engineering Conference, which is actually next year celebrating its 25th year anniversary, will be hosted from Sweden and will take place in June. We hope it will be physical. It might be online. We will see. And I was persuaded to be one of the program chairs of this conference, and I I made a decision to accept that, and I think it is a good venue, which covers many domains that could be of interest to you. Okay, so with this background, what are the challenges? There are multiple challenges, as you know, facing our societies. We have an ongoing pandemic. The indirect effects of the pandemic are likely much worse than the actual pandemic, including a recession. And then we have the great and the challenging sustainability issues, including climate change. All this is taking part of the socio-technical paradigm shift that we heard the previous speaker touch upon. And we see many facets of that. And of course, these technologies are something that we would like to use to deal with some of the other challenges, including the climate change. But there are both opportunities and challenges in these new technologies that I would like to touch upon. And so why do I talk about the technological paradigm shift? And there are many indications on that, and I will also touch upon that. But perhaps a premium example, I'm sure you touched upon that somehow during the conference. So, as you know, there's some noise. Automated vehicles are receiving an enormous amount of attention. Billions after billions are poured into this domain, going for the large budgets or needs for transportation in our society, both transporting goods and people. But what does it mean? It means we are deploying new levels of automation into very complex environments like this one here. As Herbert Simon once said, the environment is the mold of the systems we are building. So we have here a very high level of complexity. That complexity will have to be reflected in the systems we are building, including lots of sensors, including lots of assessment, reasoning, planning, lots of capabilities or features that we heard from the previous talk. In turn, to execute that, we need essentially supercomputers inside our cars. And today, I'm bringing up this example not only because it is very exciting, but it's also leading a lot of developments today. And what other examples do we have? Well, here's an interesting example from about 20 years ago, when a couple of companies, including GM and Swedish SKF, developed a concept car for a steer-by-wire vehicle. So a vehicle without a mechanical connection down to the wheels. And as you can see illustrated here, if you remove the mechanical connection, you have a mechatronic connection by wire. So information transferred over communication lines and you have separate actuators and power provision, then you can actually redesign the whole car. This opens up enormous potential, of course, all the way from safety to design. But this concept car was developed already in the 1920s. And we still don't see steer-by-wire cars on the roads. And this also gives an indication that there are multiple challenges and obstacles. And in this case, it's pretty much legislation that has been preventing legislation and probably reliability related issues that have prevented these cars. And we see the same in automated vehicles. So there has been a lot of hype on this, but the actual, it's taking much more longer time than we think. Other examples, you may recognize this gentleman. He used to be a researcher and engineer at Kodak. Kodak was a company that totally dominated the camera and film market in the analog days. It was also the company, and he was the guy leading this development, that developed the first digital camera ever. But Kodak management didn't realize that this first prototype, although crappy, not so very good performance, and so on, was to open up a completely new market and domain that they could not foresee, going from a few photos per day to hundreds or thousands of photos, going from thousands or 100,000s of cameras to cameras everywhere. So really beyond our comfort zone. And we see this in many spaces. And this is an indication of a paradigm shift. New companies emerging, old companies disappearing. We heard about risks. So obviously when we get more software, we get more connectivity, cybersecurity becomes much more pronounced. There are more ways to attack these systems. It's important to be aware, as I mentioned, that there's a strong technology push. And I like to talk about gold rush here. We see this in many areas. We see it in automated driving, billions being poured in to get to a market, to establish the platforms. Many hope to sort of grab the gold. We see it in AI with enormous investments. We see it in Internet of Things with thousands of platforms. And so essentially it means a very strong technology push. But that also, sorry, the animation was perhaps not in perfect order here. I'll come back to some of the opportunities and risks in that. And I just want to highlight here the traditional S curves that you may be familiar with. So these are traditionally used to depict performance, time, and cost trade-offs that we see in technology shifts. And I'll come back to some lessons learned on these technology shifts. So in this area, we have this technology shift going on, and we see that manifested in many different ways. One way is that we have all these clever terms being invented. And essentially, we see an increase in the number of terms. And essentially, these terms, in my view, they reflect different perspectives to the same ongoing change that we have. Just to give you one example that you may be aware of, you have, of course, heard about Industry 4.0, but perhaps not the history of how the term was coined. In 2006, the Americans coined cyber-physical systems. The Germans quite early caught on, and they had a dialogue with politicians and industry, and they said, this is really something we should do. We should go for the investments in the US. And after a while, they decided, well, we can't call it cyber-physical. That's really too abstract. Let's call it Industry 4.0. But it was actually a manifestation of cyber-physical systems in the manufacturing domain. So Industry 4.0 is a domain-specific interpretation of CPS. We heard the previous speaker talk about the domain-specific interpretation of CPS in the area of agriculture. We see similar trends in all domains and cross-cutting across domains. And I believe that, and many share my view, that CPS is kind of an umbrella term here. There is a slight problem with the term CPS, and that has to do with the etymology, the meaning of the word. So for cyber, we have at least two interpretations. Cyber, colloquially, computers, communications, well known, cyberspace and so on. But cyber originally, and in the etymology sense, really means feedback systems. It was coined by Norbert Wiener. So this has perhaps created some confusion. I think the takeaway, and as you will see, and as you heard from the previous speaker, most cyber physical systems of tomorrow will include computers, networks, and physical systems, and they will involve feedback. So this is perhaps not so much of a problem. But there are different types of cyber physical systems, different incarnations in different domains, and different facets of them, viewpoints, as nicely presented by the previous speaker. So cyber physical systems, here's the original definition: integration of computation, networking, and physical processes. As such, you will realize that this is nothing new. For example, with direct digital control used in manufacturing in the 1980s already, we had cyber physical systems. What is new, however, is that we are integrating multiple technologies, we are accumulating knowledge, and by using the capabilities of physical components, software components, data-driven components, we are creating entirely new capabilities and scales of these systems. And of course, these systems are not only cyber-physical, they integrate humans. And these systems are applicable in all domains, and there is also a life cycle across domains, and there's also a life cycle integration taking place. And as we heard in the example with automated driving, these systems are going from, let's say, more focused industrial to being deployed in our homes, robots in our homes, robots on the streets, open society scale deployment, typically going along with the business model evolution. So coming back to unprecedented opportunities and risks. And this summarizes the scope of my talk, and I would now like to elaborate a bit on the opportunities and risks. Taking one step back, of course, we are seeing advancements in many fields, all the way from the physical aspects, materials, sensors, power, to computing and connectivity. And that's really where we see the power of CPS and these capabilities when you combine these advances. And then we can deploy them as services, leveraging existing services and so on. Looking a little bit on a few examples here, automated driving is a very strong driver. That is in particular true for sensing. We see enormous investments here on new scanning sensors. Hundreds of new LiDAR companies have emerged, probably more. And that, of course, makes these systems, it drives the market and improves steadily cost efficiency. And these advancements can then be used in other domains. And as I mentioned before, this, of course, subsequently also triggers computation, machine learning, and so on. Another domain is that of connectivity and communication. And we have a very interesting situation today because we have different modes of communication. If you look at the modern car, it will have already a number of external communications, wired and wireless. But all these types of computation and communication are are sort of merging in modern systems. A modern truck will already be connected to the cloud when sold, typically to a sort of developer or operator cloud, but still with very little collaboration across islands of operators and clouds. We have another domain of embedded systems. For example, in Sweden, we had very early on connected electricity meters, as you see illustrated here. And this is just to say that one facet of cyber physical systems is, of course, the cyber side, and the world is increasingly turning into a distributed system. A new dimension in these distributed systems, we have already embedded systems, and as I mentioned, they are typically connected or becoming connected. We have cloud computing in place since many years now. Many devices are, not the least ourselves and our cell phones, are connected. A new tier in this dimension is that we call edge or fog computing, and that's very much driven by the fact that we have embedded systems with limited resources. Some of the embedded systems have very little compute. Automated driving is at the extreme level. There's a very big span. There's also a very big heterogeneity at the edge in the embedded devices. And as we go closer, we get more into homogeneous computing systems. But basically, we have the need here to do more of real-time um, assessment of. We want to use our sensors to do perception. We want to assess the state of things. We want to do planning, and many of these things are latency critical. So we want more of computing closer to these devices. And will not be sufficient. There is also too much data for the cloud to deal with. So this pushes these different aspects of distributed cloud, various facets of edge computing. Where this lands, we will see. I would say that edge computing is sort of now where cloud computing was 15 years ago. This is a very interesting area. And then, as I mentioned, we have the advances on the cyber side and the physical side. And again, an integrated distributed control system in the factory or process control is not new. They were around for quite some time. But we have new capabilities on the cyber side, much more cost efficient, standardized communication, enabling to gather much more data, more better sensors. We can do models, digital twins, and we have improved physical components, materials, batteries, and so on. And then again, we combine these and we get into cyber physical systems. I wanted to give you one example here where we are working on a test bed at KTH, which I hope has also a generalized sense of a takeaway. This is an example of smart roads, really merging how we can do roads which are cost efficient, maintained, where we can avoid things like growing cracks and potholes, together with automated vehicles and intelligent transportation systems. And we have a life cycle here. We are developing, for example, we are designing the roads at some point in time. We have a construction phase of the roads, we have predictive maintenance, and we have the operation of the roads. And if we apply cyber physical systems thinking to that, there are a number of aspects. On the cyber side in particular, we can have models of the different things in the real world. So models of the road, models of the actual creation of the road, the compaction process. We can gather data For example, through using the automated vehicles or some smart infrastructure, we can gather data when we construct the road. We can accumulate data over the life cycle, we can improve models, we can learn. Using that, we can do prediction in the short term, in real time, and in the long term. In the long term, that could help predictive maintenance. So we may even be able to we can repair the road before it breaks down. We can warn about incidents. We can coordinate traffic to improve safety and performance. I already touched upon there are quite a number of use cases you can think about here. And just to give you one example here, so apparently in road construction today, while there are new smart compaction machines that are being deployed, they are not really leveraging data and models available. So one use case is actually to use online real-time prediction to get the operator of a smart machine better feedback on how the compaction process is going. What would that mean? It means less material can be used, better roads can be predicted, achieving cost reductions, reducing carbon dioxide emissions, and so on. These examples, these are just examples, but they really leverage a lesson that can be taken across all domains. I think we heard indications of this from the previous speaker for agriculture. We can go to energy management, electrification. We can go to medtech. And it all hinges on these advances in different domains, from the physical to the cyberspace, where we can use these capabilities to deploy cyber physical systems in all kinds of domains at different levels. So this raises a number of interesting opportunities and challenges. For example, in these systems, whether we talk about smart water, smart agriculture, smart traffic, we are gathering huge amounts of data. A big question here emerges, who owns the data? Who can use the data? What are the business models for the data? What about privacy? Another aspect here is that we are creating systems of systems, meaning that we don't have a single system integrator. We have multiple legislations, multiple operators, multiple type of systems that can change during the runtime of the system, making the management of these systems much more challenging endeavor. So there are multiple challenges in this space. And I'll come back to these challenges. But before I go there, I wanted to touch upon coming back to the socio-technical shift and to how we can employ these systems to drive sustainability. So there is a nice anecdote by Herbert Simon that I quoted before, the steam engine and the computer. There he reflects on the two different what is usually referred to as two different industrial revolutions. The steam engine representing a new type of machine, and the use of horses for transport and the wagons for transportation was replaced by steam engine driven trains and by electrification. And then we have the computer era. And reflections by Herbert Simon are as follows. No single technology behind the revolution, a technological revolution or industrial revolutions. The revolutions are slow, and we shape technological revolutions. And I think, as you would have seen in my previous discussion, we clearly see a lot of different technologies that contribute to the change. And there is an indication that things are going faster, and that's not strange because we are accumulating knowledge. But for example, if we take automated vehicles, we see that we have had prototypes on the roads. We had the PATH project on intelligent transportation in California in the 1990s, for example. Things do take time. And that comes back to what we might call the hype cycle. As humans, we tend to overestimate impact in the short term, but as we had the Kodak example, it's hard to think out of the box into the future because it really goes beyond our, let's say, comfort zone where we are comfortable in thinking. There is an interesting question with digitalization. Is innovation going faster, for example, compared to the first industrial revolution? And I believe it is likely so because we are, especially when we have software and electronics platforms. Think about your iPhones or smartphones in general. When we have them in place, we can deploy functionalities much faster. But one has to remember that this relies on the platforms in the first place. And there's also a hidden complexity in these platforms. And then again, we have these combinations and accumulations of knowledge and so on. Now, as I said in the beginning, we would like to leverage these technological advancements to improve sustainability. Sustainability is a broad concept, and in this short talk, I would like to emphasize the concept of circular economy. I'm sure you are aware of it, and essentially it's perhaps more concrete aspect than if we talk about sustainability. We have economical, environmental, and social. It's a broad thing. But if we talk about circular economy, it's really about thinking, how do we eliminate waste and actually turning waste into something useful. So it's a new mindset. And it really drives that we are going away from this, as we unfortunately have had definitely in the Western world. We develop something, we use it, and we scrap it, and we reuse very little. To systems that are maintained and prolonged. And this goes very much in line with new business models. So how can cyber-physical systems help circular economy? And there are some low-hanging fruits here, or at least direct ways in which a CPS, including digitalization, can help. So what we can do, for example, by use of passive or active safe sensors, or identification, we can identify items, we can trace them through the life cycle, we can monitor them by using models and data. We can have a much better basis for this reuse. When do we want to recycle? How do we want to upgrade or downgrade or maintain our systems? The predictive maintenance example. And we have other ways of extending the life cycle using innovative techniques such as additive manufacturing, 3D printing. The architectures become very important here. And one aspect of this is that we have to think wisely so that we don't deploy electronics everywhere and we cannot reuse or recycle that. We are putting electronics and batteries everywhere, and we have to take that aspect of circularity into account. And again, the architectures becomes very important. There are lots of opportunities here. There are many companies driving this development, and I think it's also very important that we as universities embrace this topic in both education and research. And I will emphasize elsewhere, but I wanted to mention here already that The challenge here is that we are talking about technology and business models and sustainability slash circular economy. We need people from very different backgrounds to get together, to work together. We need to bridge the gaps. Okay, so coming back to summarizing benefits and concerns, we heard a bit about obstacles before. So of course we are deploying these new technologies for the benefit somehow of mankind, and there are of course also very strong business drivers. You see here the smartphone, and of course the smartphones, we tend to find them very useful, actually, to the extent that surveys show that we can't even we have a very hard time to be without them at all. But as you can see here, people are turning into zombies. We are looking into our smartphones. We are not communicating as much with real people, and we can actually be a threat to ourselves because we don't see the cars moving on. But the problem is much more complex than that. These systems have been designed, you could say, to hack our brains, use weaknesses in our brains to attract as much of our limited attention span as possible. And if we don't use these systems in a smart way, we will actually be much less effective. We have all these notifications all the time, and that really means that we will lose capacity. And there are experiments done that even if you have your cell phone on the table in front of you, even if it's not your own, it will reduce your cognitive capacity. So trade-offs there. We have introduced electronics. One example here, active safety systems. They are deployed in all modern cars. Their expansion is growing. They are saving lives. And they are also being mandated by legislation. This is an example of a very useful opportunity with new technologies. At the same time, we are making the systems more complex, meaning that they can be hacked. They have different attack surfaces, as a security expert would say. And also these systems are complex and they will fail. Here is a view of the Uber car that was on test and it crashed. Here is an even more perhaps scary example, the Boeing 737 MAX example. We had 2 accidents with modern aircraft. And why is this perhaps particularly frightening? I would say it is so because the aerospace avionics domain is one of the most mature domains when it comes to control systems and safety. And here they introduce a new control function and suddenly they make all kinds of mistakes that they should not really do. If you're interested in this, you should really look at this example, and it highlights the need to remember the automation, the so-called automation paradox, which still is very much relevant. So we have these benefits and new systems that introduce opportunities, but also create new risks, sometimes with hidden business models. And a very relevant example here is the so-called digital surveillance economies, where a known example is that of Pokemon Go, which apparently was driven by Google, not always obvious to all, and with a hidden business model behind it, not only gathering data, but also controlling to some extent our behaviors. So with these words, I wanted to, there are many challenges the challenges can be made very long. And I have just touched upon a few here. I would just to raise a couple of more examples. So we are talking much more about data and software-defined functionalities. And with software systems, we can really build unprecedented complexity. Software development goes seemingly fast because we leverage software libraries, software components, software tools. But this is typically done by building layers of abstractions, adding complexity. And this means that future systems, current systems, they have a lot of bugs. They are sitting there waiting to be triggered. Then we have data-driven systems where we have had tremendous breakthroughs. We don't fully understand these systems when it comes to their robustness. And that means that these systems will work well in non-critical systems, and we already have them deployed. But they are much more controversial when it comes to availability critical, mission critical, and safety critical systems. So these were examples of challenges, and here is the third challenge I would like to raise. So with automated driving, we want to, using the terminology by Kahneman, we want to not only have smart mechatronic systems like we have in our bodies with excellent actuators and motion control and coordination. We also want to think fast, the recognition, let's say the machine learning systems. And finally, we want to deal with the unknowns. And we want to put that into autonomous driving intelligence, whether it's robots on the streets or in our homes or elsewhere. And today we can program, we can build mechatronic systems, we can do these systems, whether they are rule-based, ordinary software, or even machine learning-based. But we can't really program, and we don't really know how to deal with the unknowns and the generalizations that humans are known to be quite good at. So this really emphasizes a challenge in deploying these kinds of increasingly complex systems. And that really leads to perhaps the biggest challenge. We are developing these complex systems. Are we as humans ready to deal with these systems? What are our abilities? What are our limitations? Recent research we are learning much more about the brain, and there are very interesting results there. And as humans, we know that we tend to divide aspects into categories. We see it everywhere. It's a way to sort of manage complexity. We see it in scientific disciplines. We see it in the military. We see it in industries. And that's useful. But it is devastating to our thinking out of the box. We have to make sure. There's also this thing called groupthink. It's very easy when you come into a group of people, whether it's a discipline or a department, you go together, you think along others, and it's very hard to get out of your box. And because we are, as we heard from the previous speaker too, we have these different viewpoints. We have many views, many aspects. Managing this is crucial. Humans have difficulties in dealing with feedback systems and in systems with multiple time constants. That is, to my understanding, a way a characteristic of how our brains work. And we know also from Kahneman that we are not primarily rational. We have these emotional aspects. And that means that even if we have the right data, the right decision, we may not actually take the right decision. And perhaps a concern on a larger scale is that we have evolved to take decisions in small groups, and now we are dealing with society scale challenges, both for example, climate warming or undecided effects of digitalization. So these are key challenges that we need to deal with. And this really means that we need to look for new methodologies to develop these systems. When I did my sabbatical at Stevens, that was one reason. One reason for that was to engage with the systems engineering communities, and they are very well aware of this, and they are striving to develop. Systems engineering as a discipline was developed in the US to deal with complex systems, but primarily physical systems, not cyber physical systems. And so what we need, we are developing systems with much higher requirements. We have humans, we have cyber, we have physical. We want them to be trustworthy in a broad sense. Humans should be able to trust these systems, regardless if we talk about privacy, security, or safety. We have to take many aspects into account. These systems will have to be learning because we are deploying them in much more complex environments. So, for example, when it comes to security, learning is sort of the standard practice. We are upgrading software systems. When it comes to safety critical systems, they are typically not upgraded, but they will have to learn too. We had to deal with very large design spaces, complex environments and operations. We can draw lessons learned from different sciences, like socio-ecological systems. And as I mentioned, perhaps the biggest challenge is actually how to have humans to collaborate and have AI, computer-aided engineering, and humans to work together to combine our capabilities to deal with these complex systems. And again, highlighting really the need for multidisciplinary and socio-technical efforts. I wanted to highlight here the need for balancing the level of complexity that we put into these systems. So obviously, we are buying these systems. We don't think of these systems as having billions of transistors, but they actually do. They are ticking at speeds of gigahertz. We don't think about that complexity. We have cars with 100 microprocessors or more. In some sense, we sometimes we want complexity because that gives us new capabilities, but we want to balance that. And here's a quote saying that, I think this quote is perhaps more from the software side, but as I mentioned, it's all too easy to build with cyber systems, to build systems that are much more complex than you would have thought about from the beginning. And then you have to manage these systems. There's a nice new book by Herman Kopotz. The book is called Simplicity is Complex, meaning that coming up with this also is kind of related to Einstein's known quote, coming up with systems that are complex enough, not too complex. That is really a challenge. And I have a nice example here, or let's say a lesson learned. I had the opportunity to meet Bill Shepard, first commander on the International Space Station, and he had the example of the toilets on the International Space Station. And why did you raise that example? The example goes as follows. So a nice example of the space station is that we have international collaboration. So for example, Russians are working with the US and they are deploying technologies. And now it came to the toilets, and the Russians had toilets they wanted to promote. The Americans had toilets. The American toilets were extremely sophisticated with lots of software, lots of microprocessors. The Russian ones were more physical, more modular, and more robust. Guess which toilets worked up in space and were maintainable up in space? I'm told that Russian toilets are now deployed in the space station. So this is just to say that we need to balance this complexity because we need to maintain and manage these systems over the life cycle. So I've touched upon a number of opportunities and challenges. And here briefly, before wrapping up, I wanted to mention some of the things we are doing at KTH. So because we are embarking on future cyber physical systems and systems with lots of unknowns, we have to learn more. We have to put some emphasis on test beds to get stakeholders together to learn. And here are two examples of test beds that we are working on at KTH. We are also putting a lot of emphasis on getting disciplines together and industrial partners together. And for example, I had the opportunity to lead the IRIS initiative in its startup phase, and there we are putting together researchers that work all the way from new materials, industrial production, business models, to smart systems to work together. And this is not easy, but this is something we are really driving there. And I'm happy to elaborate more if you have questions. We have the recent TACOSA Center, which puts together researchers on trustworthy edge computing systems, all the way from human-machine interaction over security to safety and machine learning. And you heard in the introduction, many years ago, I created this competence network, ICES, and it's a competence network to make life easier, for faculty and industry. And we focus on how can we improve education? How can we develop lifelong learning? How can we create new multidisciplinary projects like the COSA? And yes, and basically that's an example where we are emphasizing the things I have mentioned so far. They sort of, there are many different aspects of them. One important aspect in particular for us at industry is that this is, I think, a time to think about educational renewal and about lifelong learning. Of course, the pandemic has triggered this even more with online learning, but that there is also a way to reflect together with stakeholders. What is the shape of a future engineer? What does a future engineer need to know? And just to give you one example, I'm developing a new course on cybersecurity and safety. So this is an example. We have multiple courses on cybersecurity at KTH. We have courses on safety. We have so far no course that combines these. And we have computer scientists that learn very little about physical systems and safety. We have embedded engineers that learn too little about security, just to give you one example. And I want to wrap up here. I guess I am on time, assuming that we started a bit too late. So I started with these challenges, and there are many reflections on this. I think thinking about, you've probably heard about the concept of T-shaped engineers coined in the 90s. So developing engineers that are not only they have an in-depth knowledge in one domain, whether it's mechanical engineering or software, but they also have a broader understanding of other disciplines, and they can collaborate. Equally important, we need T-shaped researchers and engineers. We need to balance the complexity. We need collaboration and multidisciplinarity. Systems engineering and systems thinking is important wherever we go. We need to drive for open experimentation and how to deal with data, and we need to promote a circular economy. And with these words, I'll be happy to share my slides if you want to put them online. I have some more references in there. And with these words, I would like to conclude, and I would like to say thank you, Nandri, and Shukriya. You are muted, Dr. Nisha.
Yeah. Thank you so much. Thank you, Professor Dr. Martin. It was a really, really wonderful intellectual talk, and it's a vast, huge presentation to look. It was really interesting to listen to you. The floor is open. Participants, if you have any questions, you can ask, unmute yourself and you can ask. If not, you can put it in a chat box. We will take it up the question to the speaker. We will email him so that we will get e-connected.
Yes, questions are welcome now, or you're also welcome to come back to me afterwards.
Yeah. Okay. With your permission, Professor Dr. Martin, I'll collect the questions from the participants along with Mr. Rajkumar sir. We will email you. Once we get a reply, we will be forwarding the same to our participants. Is it fine, sir?
Yes, that's fine.
Okay. Okay. So once again, on behalf of VIT Business School Chennai campus, I thank my heartfelt thanks to you for participating in the conference and giving such an insightful talk here. Once again, thank you so much. Thank you, sir.
Thank you again for the invitation.
Yeah, thank you so much, sir. Dear participants, thank you for your patience listening. We will join back by 3:30 p.m. for a validity function. Herewith, I close this session with a thank note. Thank you, Professor Martin. Have a good day.
Thank you. Bye.
Thank you, sir. Bye.